So, ladies and gentlemen, for this session, we'll be using 3 sets of documents: document.txt, non-health related tweets, and health related tweets, which are classified by me manually. And we're going to put them into a very special place. Okay? We're going to put them into the data area of our Spark folder. So if you're in your Spark folder here, and I'll quit out of it, there should be you should make, if there isn't one already, a subfolder called data with a lowercase d, D-A-T-A. And in that, you will put each of these components, document.txt. Actually, there should already be a folder called that, I think, in your Spark folder. And you can put each of those in there, each of those files, okay? We're going to be loading them in from there. Now, if you were running Spark in a production way, like on a farm of machines, you'd want these to be put in that data directory of each Spark's installation, okay, so that each of them could load it in from the corresponding place. Here we're just doing it on our own, okay? Yes, go ahead.
I may be bring some things, but couldn't we just as easily have Spark, like we transform the data in some way so it becomes a, like, I don't know, word vector or word vector, stuff like that, to the point, and then have the pipeline send it out?
Have it send it out to different machines?
Well, I mean, if you make the data that you're actually performing the machine learning on, part of the package of what you're,
I see.
Kind of thing.
Yeah, in the pipeline you're saying.
Yeah, exactly. And then you would just, when the pipeline gets sent out, it would send with it, right?
Well, yeah, I see. Could you package it with the pipeline, you're saying?
Right.
Yeah, you it's an interesting one might be able to do that. I'd have to think about how to operationalize that.
Well, the reason I asked is because,
yeah.
What you want to do with, making an analogical model a transformer, there's no way you want to actually put your model, much less data that it needs,
right,
in every single machine you might be using. So we would have to tackle that if we wanted to do it. So,
yeah,
just as a point. That's why I asked.
Yeah, I was kind of assuming you would do that, but okay. So let's move on. So good question, and I'd have to think more about that. It's an interesting idea. Could you do it? I think you could in some form. Okay, so we're going to start up Spark here. Okay, and as it's starting, I want to rehearse some things that we saw last time. Okay, so last time we talked about here the use of pipelines within Spark. Okay, these pipelines. Whoa. Okay, these pipelines accompany a set of mechanisms. So they accompany the ML machine learning library, which also comes with a set of mechanisms for data wrangling, transformation, and conditioning. So often in a given machine learning process, yes, you're running a machine learning algorithm at the end. Maybe it's a support vector machine, maybe it's a neural network, maybe it's a logistic regression, maybe it's a decision tree. But prior to that, often there's a set of stages of data processing where you're going through, you're throwing certain data away, perhaps with outliers or data which has missing data. You're potentially bringing in the data from a source. You are going and processing the data by standardizing it, by normalizing it, or by standardizing it in terms of making it zero-centered for its mean and having a standard deviation of 1. As it turns out, today we'll see there's often a lot of processing on the text side that we'll further do to take text, say from tweets that are received live, or say from tweets that have been archived and classified already, and that process them, they munge them in various ways. So they tokenize them to turn them into individual words. They remove the most common words like articles, a, the, an, and they turn them into just the base words. They turn them into vectors based on the presence or absence of a certain word, or they compute pattern, like pairs of words or triples of words that go together that are contiguous. Yes, go ahead.
Does stop word remover actually remove the word
Uh,
as a conjunction?
I think it does, yes.
Because that
but
that might be an issue
I'm
if
not
you're trying to classify
Yeah.
tweets. Because if I say the word button in a tweet, I'm responding to another tweet.
Sure.
I'm probably anti that other tweet.
For sentiment analysis, it could be a problem. Absolutely. For sentiment analysis, this could be a problem.
Another question
yeah.
I have is that most of this you're doing all the data processing and then you're performing the machine learning at the end.
Yeah.
What happens, like for example, in Markov models or particle filters, where the model that you're building, we're using simulation to do? I mean, what I'm sounding is like we have to actually compose the pipeline of the data with the model to get the actual machine learning to happen.
Well, it's quite common that you might have multiple models in the pipeline.
Okay.
From one going from the one to the next. But the pipelines are stateless pipelines in the sense that they are independent of state. And I think the way Spark is going down the road, stateful pipelines will increasingly be incorporated, like with hidden Markov models and so on. But right now they are stateless, and they are functional. You apply them to you apply them first to a data set to estimate them, and then you apply the resulting model, which bundles all the features of the pipeline together. You apply it to a data frame to get a data frame out. Okay, for the estimation, you put in a data frame, you get a model out. For the model is a transformer, and that takes a data frame and gets out a data frame. Okay. In addition to those things, and you also have recourse to things like principal components analysis, standard scalar, max min, and we talked about these last time, including things to histogram, essentially histogram bin data. These are really useful. Okay. Now Spark pipelines, we talked about last time, so they're simultaneously both a higher level construct to encapsulate a set of operations in a row, so we can apply them. But equally importantly, what comes out of a pipeline is a model that incorporates the knowledge of all those steps. So when you take a pipeline and you use it as an estimator, you fit it. Remember, fitting is the word used rather than training in Spark ML. You fit it to a data frame. Out pops a model. And the model is a transformer. Remember that things in those pipelines and things in Spark ML, some of the most important things are either transformers or estimators. Either estimate a model or they can transform a data frame. Maybe they are models that transforms a data frame, or they're one of these things here that transform data frames. Okay, the model that pops out when you fit a pipeline, you do pipeline.fit to a data frame as a model. It's been trained on that data, but it's a special type of model. If your pipeline had a long sequence of operations, maybe involving many of these, and at the end of it, say, is a model, a logistic regression model or a neural network model, when you fit that pipeline to data, what you get out is actually not just a logistic regression model or a neural network model. What you get out is a model that takes data and applies it through these operations as given of the whole pipeline, and then applies the tool. So you get out not just the fit version of the final model in the pipeline, you get out the full pipeline. And often these intermediate steps in the pipeline themselves have to be fit. So as we will see, for example, the count vectorizer here, this guy here, we're going to need to train it on a vocabulary of tweets, a tweet vocabulary. And it's going to remember that tweet vocabulary, and then we're going to apply it to a different data set where it's going to be creating them as vectors based on the tweet vocabulary it was trained on. It's going to be categorizing them in corresponding vectors. So in short, in these pipelines, there may be several components that need to be estimated, that need to be trained on data. And there's a training phase, and out of that will come a model that remembers the entire pipeline and remembers all its results of training. So when it's applied to a data frame, out will pop a data frame from it. You can apply it to the data frame of the raw data, and it will go through all the stages of the pipeline and pop out results. Okay, from the trained models along the pipeline. It may include multiple models, it may include multiple estimators, etc. So there's going to be a training phase of the pipeline. Out of that comes a transformer or model, which can then be applied and encapsulates the full stages of the pipeline. So it ensures, in short, that both the training step and the testing step operate on the identical pipeline steps. Yeah. Scott, did you have a question?
So I mean, I understand the value of this in terms of keeping everything together. So all I had to do is I had to send in raw data, and out comes the analysis of that data.
Yeah.
Right. So like Dylan's thesis, as I'm sure we're going to do.
Indeed.
But you're losing something by doing so, it seems. Because, I mean, can I, for example, what happens if I'm interested in what the count vectorizer was fit as? Can I get that out of this?
Yes, you can. We'll see how you can do that.
Okay, because I'm just worried that, I mean, atomizing things is useful in terms of, keeping it all together, but if you start losing some of that...
Pipeline is a higher level abstraction. You can always not use it.
Right.
But you can also extract elements from it, and we'll see how that works. Okay? So it's not monolithic.
Well, like, for example, I would love to train this on 2 different data sets and see what the actual differences in the actual model is.
Yeah,
for example.
You can do that. After data session, you should be able to do that.
Okay.
Okay, so let's start up Spark. Okay? As some might call it, Sparky. Okay. Okay, we're starting up this. Okay? So, are you folks ready with Spark? Okay, ladies and gentlemen, we're going to go and we're going to go. This is the second item I sent you. This is a simpler one. We're going to go and go through the full set. So I sent you 2 messages. One is the first one was the one we're going to be going to after this. The second one is the one we're going to start with which we're going to start. Okay, so I'm gonna put this in there. So apologies for their out of order. Here we go. Okay, so I just imported. This is all the sort of the boilerplate. Okay, just did that. Next, we are going to go and we're going to read in. Well, we're going to read in from this text document. And what are we doing here? What are we doing? Well, it turns out when we read it in, we're going to get a data set of strings.
And we're removing everything that's length 0.
Yeah, the strings of length 0. And the fact that we're doing this, what does this tell you? This is something I've been neglecting to enforce, but it's actually quite easily layered on what we've been doing the past bunch of weeks. We're operating here with a fully typed data set. And it's very easy to do that in Spark by saying, treat it as an instance of this case class. So here we go. Okay. Okay. Okay, so that's interesting. Let's do a thing here to debug that. I'm not sure how that came through. Print schema. Here we go. So we're reading it in. Come on.
Shouldn't take that long to read Dylan's thesis.
You believe me, it took me a long time. Okay, it is value, yeah. So this is so that's true, but it's an RDD of strings, I guess, is its point. So that's fine. So I think we could just go basically like this. Yeah, here we go. There we are. So it's an RDD of strings, okay? So here we go. Let's go take a look at DSDoc. How are we going to do it? What do I do to look at it? What do I do to show it? Show. Okay, here we go. Okay, and I don't know what's, hello? There it is. Okay. This is a filtered thesis, right? And of course, you can parameterize this if you want to see the first 100 lines. There we go. Okay. Great. Okay. Next, we are going to use some of these mechanisms of which I spoke, these mechanisms here. We're going to be using them. We're going to get a practice on them here, and then we're going to use them in a more fulsome way to classify these tweets as part of pipeline. Okay? So here we go. Part of a logical pipeline and maybe arrayified pipeline. Here we go. Okay, so I don't want to go there. Okay, so what we're going to do is we're going to create a word splitter. It's actually technically called a tokenizer here. And that word splitter is going to need input from one source, and it's going to put output in a different column. So this is the column from whence it gets its value. This is the column to which it puts its value. So I'm going to do print schema here. Okay, here it is, value, yeah, and I'm going to create this word splitter. Now this word splitter, by so doing, is it splitting up the words already?
No.
No, ladies and gentlemen. Word splitter is a transformer. To do its work, it needs to be passed a data frame, or in this case, a data set. Remember, a data set, as of Spark 2.0, is just a fully typed data frame. Okay? So here we go. We're going to go do that. We're going to say wordsplitter.transform, and what comes out of wordsplitter.transform is what? Well, here we go. It's something strings and tokens. Here it is. Do you see what's happened?
This is like when we had it map it.
Yeah, it's a little bit like that. That's right.
Can we just flat map it instead?
We could flat map it, except that here I think it's actually, this is an array on each line, so it's preserving the line structure.
Right.
Flat mapping would make each of them in a different element of the RDD. But yes, that would be another way to pursue this, but my goal here is to show how we can use these tools. So
sure, I'm just noticing similarities
so,
to what we were doing.
Yeah, so you'll notice that it's tokenized in the sense that now we have each word distinguished as part of an array. Do you see that? This holds an array. It's not just a string of text. It's an array of strings. Yeah? Array of strings. Okay. Great. Now we're going to create something that removes trivial words. And this is based on stop word removal. I guess a stop words removal. So this is used to eliminate words that are extremely common and may not be adding much to the analysis. They also happen to be words that many international students find challenging, and so you may be happy to see them go. Yeah. No worrying about a and an, or when to use the versus a, and all that sort of stuff, which has bedeviled you.
I find that very interesting because other languages you can't do that.
Well, I think some other languages.
Well, I was thinking, in some languages you can, but like for in Japanese, you cannot remove the actual
right, because it's
modifiers for the words. In fact, I'd almost say that you keep the modifier with the word that you're modifying. So like,
sure.
Watashi wa versus watashi ga actually means something different. So.
Yeah. Yeah, no, I agree. I mean, it's a thing with English. Now, this is not the only way to downplay these common words. There's another technique that I'm not showing today. It goes along with another one we'll be using shortly, which is associated with turning words into vectors. Okay, and it can associate lower weights with words that are very common in the text. It's called IDF, inverse document frequency. So basically, you can be looking for words that are common in this tweet, but uncommon in the rest of the text. And it downplays words like a or the that occur a lot. So that would be another way to deal with them instead of removing them. But I want to show you this. So here's the trivial word remover. Now, has it already removed the words? No, it's a transformer. We have to transform a data set. So let's go transform a data set, ladies and gentlemen, okay? And you'll notice that first I do the word split here and then the trivial word remover, okay? So I'm just illustrating how we undertake these things. Okay, here we go. So here's the original one. And you'll notice what's happened. As we've applied each one, what has it done? What has each one done?
Create a new column.
We've created a new column, ladies and gentlemen. We've created a new column. You notice there's this input column. That's from whence it comes. And this is the column that it creates, right? So here we started with this. Here are the tokens, and here are the more significant words. And you'll notice a bunch of words have been removed. Can anyone spot a few words that have been removed?
The and of.
Yeah, the and in, I think, right? The for the degree. By has been removed, right? Head department. So, ladies and gentlemen, this has removed a lot of the most common words. It's not the only way to do something like that. There are more subtle ways, but it's one way. Okay, good. So let's do a few more of these. Here's ladies and gentlemen, a tupleizer. Okay, here we go. We're going to create a tupleizer, okay? And we are going to use that to tupleize these words in this text. So here we go. And you'll notice, what is this? How does this differ from that? They're bigrams, ladies and gentlemen. Yeah, they're bigrams. Now, it's my understanding here, and I've actually not. Here we go. Here's set n, right? We could do trigrams, bigrams. First, I want to let's go take a look at this. Let's do. What is it? Take the first 5, and then let's to array them, right? To array them, or to vector them. Okay, here we go. Okay, so here we go. Ladies and gentlemen. Okay, we should have selected, sorry. We should have selected, that's called the bigrams column. So let's go select the bigrams column before we do the take. Select bigrams dot take 5 to vector. Here we go. Here we go. So here are bigrams. Design use smartphone data, collection tool accompanying configuration, graduate studies research.
I can see why you'd remove the words instead of using IDF on it if you're doing bigrams.
Yeah.
Otherwise, you'll get a lot of bigrams that just have half the information is useless.
Yeah. Okay. So let's go drop the first 1,000 and then take 5 here. Okay. So what's the matter with drop? Okay. Oh, there's 2 drops. Okay. Hello. Oh, of course. Let's do it. Let's do it here. No. We want to do it. Hey. Okay, it can apply to column or it can apply to data frame. Okay. I want it to apply to the data.
Could you make the just like bigrams? Can you make it a stream and then apply those?
Well, here maybe I can. Can I do? I don't think this will work, but let's try this. This is an interesting thing. There's probably some easy way to get it to know which one this is. Okay. Okay, so cannot be applied to int. Oh, okay. Okay. Drop. Okay, that's interesting. What is it? If it's not drop, what is it? It seems drop is used to drop a column here, which is not what I want. I want to skip. Is it skip? I can't remember with data frames. I'm getting it confused with regular connections. Okay, no, skip. What is it that you can do here to? I thought it was drop, but come on. Show, roll up, limit, no. First, no. Yeah, I thought it was drop, but it's an unhappy camper. Yeah. So it doesn't look happy here. Probably I can do last. No. Tail, no. Take, no. Okay. Okay, that's too bad.
I think you could just use, like, can you take the column, then convert it to a stream or something else like that, and
then drop it?
Yeah, that's what I would sort of do. Can you do that?
Sure. Yeah. That's not a bad idea. Okay. To vector, and then do drop 1,000, and then do well, I don't know if you can take from that. Drop 1,000. Let's oh no, I'm not a member of data frame. Okay, to vector. Okay. Okay, that's okay. Well, this is not worth fighting. Okay. That's curious that it's yeah, take the first. Well, fine. We'll do the first 1,000 of these. Yeah. Okay, there should be a way to drop the first bunch or skip them, but I think we'll have to move on. Okay, so here tupleizer. Let's turn our tupleizer into instead into something that computes triplets. Okay, set n here, and we will set the output to be trigrams. Okay, and here we'll go and transform this and show the first 100. Here are our trigrams, and they are sort of cobbled together from 3 different ones at a time. Okay. Okay. So, right. Collect, drop 1,000. Okay. There we go. Yeah. Collect, drop 1,000, and then we can look at this. Okay. So here we are seeing. Yeah, this is all columns, unfortunately. So what we really wanted to do is select trigrams, collect, drop. Here we go. Boom. Here we go. Yeah. Data on server databases. On server databases, data. Databases, data storage. Types, media architecture, LLS. Coordinates, variety types, etc. Okay? This is, here we've taken this, we've collected it, and we dropped the first 1,000 and saw the rest. Okay? Great. So, trigrams. Here we've applied these successively to data, and we've seen how they're transformers. They take in a data frame, and they put out a data frame. Okay? Very simple, basic idea. Before I go on to the next one, which I sent you, I was thinking actually it might be good if I introduced one of the items which we'll be using. Okay? And that is, and if you want to open that one up, you can go paste this in. There's a thing called the count vectorizer. Okay? It's from the other file, but it's in this partway down called the count vectorizer. Okay, and I have it called map words to presence absence vector. Okay, so this is different from what we've just seen. What we've just seen are transformers that right out of the box can be applied to data frames. This new thing is different. This new thing is not itself a transformer. Instead, it's an estimator. But like all estimators, if you train it on some data, it'll output something that's a what? Transformer. Okay? So this estimator, mapped presence absence vector, we're going to be able to give it some data to fit. Okay? We're going to give it data from the results of this stuff, this trivial word remover, all that sort of stuff, okay? And maybe to just make it easy, I'm going to do val words, equal to that thing here, words, okay? And we will see here, is it able to process this? So here we have this map words to presence absence of a vector. And I will try to, I've actually never done this manually in this way, but I will try to fit it to a data frame. And what data frame? It's called, I should have called it DF words, but it's named here as words. Okay, boom. Oh, you don't. Okay. Here we go. Okay, so ladies and gentlemen, you'll notice what this spat out. You'll notice out what this item spat. What did it expectorate? It's a vocabulary or a what do I call it in this other? Well, I actually didn't call it here. It's maybe I'll call it a vocabulary vectorizer model. Here we go. Boom. I've just trained it on some words. Said, hey, these are the words you need to pay attention to. Figure out how to turn them into vectors. Each of these words. Okay. Now, that's a model. And what is a model in Spark ML? It's a what?
Transformer.
It's a transformer. It transforms data sets, ladies and gentlemen. So we can apply it to, well, words. And here we go. Okay, transform words. And I'm going to do show. And out of this is going to come something that looks something curious. What column did it add?
Features column?
Sorry? It added, ladies and gentlemen,
Where's the pool table?
The features column, okay? The features column. The features column. And what you actually see there
Numbers.
is perhaps puzzling, but if we go and we look at the schema, its presence may be further explicated. Ready? Here we go. We're going to do print schema. And what you'll see is that features is a vector. And what you see illustrated there is what's called a sparse vector. That's a sparse vector. Okay? And how many items are there in all those vectors? They're actually all of the same length. 2031. Okay?
Oh, okay.
And these things here are part of a first of two arrays that are part of a sparse vector, okay? The first array denotes which which entries are actually filled in with non-zero values.
Oh.
The second array indicates what are the values for those entries. So
So what this has done is it's created it's basically created a vector for every item you have.
yeah,
And is specifying in vector form
Yes.
what words were in that.
correct.
Why?
So that we can fit a logistic regression model
Oh, well that's something. Yeah.
that classifies the significance of each word.
But with 2031 items you're trying to classify, wouldn't you need a lot of data for that?
Yes,
Okay.
we're going to have a lot of data.
Oh, okay.
Okay, so ladies and gentlemen, we're going to select here features, and we will do, and we, in fact, we'll do take one. Okay, this is just going to give us one, right? And you could see it there in its fulsome glory. And I will do collect here. Hey, okay, this is an array of row. Okay, forgive me for just a sec while I frob this. Okay, yeah. So I need to unrowize, and I could do that if I wanted to, but that's fine. You could see one of these in more detail. So you'll see that each of these guys here, 1, 2, 3, 4, indicates the number of times that word appeared. The word, how do we know? So word 0 appeared one time. What was that word? Well, it might have been design. Word 9 appeared once. What was that word? Use, maybe. Okay? And there's 2,031 different words. Okay? That are being used here after we've removed the stop words and so on. So it seems. Okay. Okay, ladies and gentlemen.
The length of the vector is corresponding to the longest one, probably, not
the longest.
the longest line which had the most number of the words inside.
So the longest distance in the
For the other lines, it puts just zeros. That's why it's sparse.
Yeah, but I think actually it's, so watch this. Let's go to this vectorizer model, and let's go look at, and we're going to go look at its vocabulary, okay? So count vector model dot vocabulary, okay, vocabulary. Here's its vocabulary, okay? And we can do size on it, and it's 2,031 words that it knows about. And these are the words: data, sensor, used, task, system, collection, use, IEPI, SIDACO, health, given, activity, processing. Those are the words it uses. And each of them, ladies and gentlemen, has a position in this vector. And, each of them has a position logically in what this vector denotes. But this is a sparse representation of it, okay? This is a sparse representation of that vector. And as such, it you'd have to imagine that it goes from 0. It stretches out, and then there's the ninth one is, so it's 1 first, and then 0, 0, 0, 0, 0, 0, 0, 0 up to index 9, and then 9 is 1, and then 0 up to 52. And each of those successive values indicates one of these words. This is word 0. This is word 1. This is word 2, word 3, word 4. Okay? Word 5, word 6, word 7, word 8, word 9. Right? So here we are denoting the sort of vocabulary associated with this. Now, meanwhile, there's vocab size here. Okay, this is actually a parameter, sorry. So that's not going to be that helpful. Okay, so this lets us know what the vocabulary is on which this is trained. How does this remember this? Well, because we fit it to a document. So it extracted this vocabulary. And now it can apply that vocabulary when we transform things, right? When we go transform it, we can extract that. Okay? There we go. Boom. So this is the transform version of this line, that line. So it's encoding each line now as a vector where a particular vector index, x, y, z, etc., the successive indices in the vector denote a specific word and how many times that word occurs. That's why it's a count vectorizer. Yes?
Sorry if I'm going slow here. So if we're going to fit this to logistic regression, what's the logistic regression going to tell us?
It's going to tell us the significance of that word in predicting whether it's a health-related tweet or not.
Oh, okay.
Yeah.
I thought we were still on Dylan's thesis. My bad. I must have missed that.
Well, I'm doing this to prepare you for the full
Okay.
task.
Okay.
To explain each of the components we're going to be using for the full
Okay.
task, or many of them. Okay,
Sorry.
so we've just seen how we can process text here with these successive transformations, and I want to draw your attention once again to the fact that we are using these text processing data wrangling things. But we have no machine learning task we're undertaking right now. We're going to be undertaking that next. Okay? So these are examples of text processing transformers or estimators that, being trained, can return a transformer. Tokenizers, we saw that. Count vectorizers, we saw that. N-gram. Stopword, remover. And TF is a little bit like count vectorizer, except it unfortunately doesn't keep the vocabulary around for you to query it. Okay? There's also a thing, word to vec, that sort of summarizes the words used in a document. Okay, so let's go back here and let us quit out of this. We quit Spark, and now we're going to re-enter Spark. We quit it because we had cruft created, and I just want to start. So we are transitioning from the first code I sent you now to from the second code I sent you to now to the first code. Okay? We're going to that first bit of code I sent, which is a longer piece of code. And the pieces that I've just shown you should help you understand what this code is doing. And this code very much has to do with building up tools for doing logistic regression on tweets. Okay. And we're going to see more how to use those tools we've just seen, but in a pipeline context and in the context of cross-validation. Okay, so here we go. Ladies and gentlemen, I'd like you to go through all the stock steps down to this, and including import SQL context implicits. Okay? Here we go. I'm going to do paste here, and I'm going to do boom. There we are. There we are. Next, we are going to read in from that data folder. That data folder. We're going to the data folder within the Spark folder. We're going to read in these non-health related tweets and these health related tweets, which I classified. Just to give you a glimpse of what these look like, I'm going to satisfy myself by just showing you the health related tweets, because the other ones aren't worthy of being shown. Okay, here we go. So I'm going to go up, and you don't have to open it, but here we go. Health-related tweets. Okay, I hate being sick. Why did I have to get sick? okay for hygiene when someone's sick. Everyone I know is sick.
So I'm thinking one word out of here immediately.
Pandemic influenza, impact of vaccination cover of critical illness in children. Okay, that speaks to me. Quit buying diet stuff. It's poison, causing you to be more ill and fat. Eat the best of food. Eat to live. Okay, this was a hard one. The one holding the flag was dead in a week of scarlet fever. The good old days, hey? Why do our taste buds go away when we're sick? Update in college. Everyone is starting to get sick again. It's happening all over again. So it paints a somewhat grim life. Searches medicine cupboard for cough mixture. I have been ill for over a week, and now I really badly want to have a sick day. Okay, I'm not going to repeat the full thing. Anyway, lots of health-related things there. These are of a variety of stuff. There's a variety of things. And there was someone here I wasn't actually sure they were health-related, and I just had to use my best judgment. I did include mental illness as a health issue for sure. I included, sort of more comments on health issues, but there are some in here that I had to confess I'm not sure. I think the entire swim team is sick, etc. Okay, so here's health-related, non-health-related. We're going to try to classify automatically which are health-related, which are not health-related, okay? Using a machine learning classifier. Okay, let's go over to our Spark. We steel ourselves for the task at hand. Here we go. Okay, so having done that, let's read in these two sets of data. Ready? Here we go. Boom. I'm just reading in the health-related tweets, and I'm reading in the non-health-related tweets. Okay? Here we go. Is it reading them in? It's promising to read them in. Okay? It may be peeking at some of their structure or what have you and figuring out. But in any case, labeled. Okay, now we're going to label them. And the trick here is I know what these are because I classified them myself. So I know all those that are in the health-related are labeled 1, and all those that are non-health-related are labeled 0. Okay? So I'm manually saying, those are my labels for training. Yes, Scott?
And then we can just stick them together.
Yeah, we're going to stick them together now. And we do that through union. We're going to union the health-related tweets with the non-health-related tweets. Okay? Here we go. And that creates all tweet texts. Okay? How many do we have of each? Well, you can go count if you want to. I think we have a goodly number of each. So here we are, health-related tweet texts. Now it has to read them in at least enough, 104 of them. How about non-related, tweet-related text? How many of them? 399. Okay? Okay, I harvested about 500. Okay, here we go. Okay, now I'm going to split them in right now manually. Later we'll do it automatically. We're going to split them into two halves. One, we're going to split the set of all of them into two halves. One is going to be for labeled subset 1, one labeled subset 2. So we can do a sort of cross-validation. Okay? Did you get that? Get or not? Do you like this style where I give you the code ahead of time so you don't have to type it in? Okay. That will speed it up next year. Okay. Next, we're going to define a word splitter. Did we see a word splitter before? Tokenizer. Yeah. Yeah. Not 1 hour thence. We saw it. Okay? So let's go transform it and let's see what we see. Here I'm doing the I'm doing the first half. health is not okay. Oh my gosh. Okay, I don't want to even comment that one. Bed all day, been feeling, being sick isn't, having a mental, I'm so sick. Okay? So these are sort of tokenized versions, just like we saw for the Dylan thesis, except that they lack the gravity and erudition of that thesis.
Well, I mean, that's something very specific to Twitter.
That is, yeah,
Because
indeed.
if you have 140 characters, you're going to use short words.
Right.
Like I would almost expect everybody to use sick instead of illness.
Yeah.
Although no one, but I think like I'm going to use ill over sick.
Mm. Okay, so trivial word remover. Where have we seen that before? What did that one do? Remember we saw it? Yeah, it just removed all the most common ones. Here we are. Okay. Okay, so it removed why did I have to get sick to get sick. It went quit buying dying to quit buying dying. And you notice diet. You notice I think it also standardized their capitalization. So it's more canonicalized. Ladies and gentlemen, next we're going to map these words. Well, we're going to put in the mechanism to map these to a vector. Now, here we go. Map words to present absence vector. What is this thing? Is it a transformer or an estimator? This count vectorizer. It's the thing we've dealt with before. What is it? What is this thing? Can you remember? The count vectorizer. This was different, I argued, than the others we saw in the last one. Why was it different? Ladies and gentlemen, it was a what? Well, if you can't remember for sure, you can go back and look. Here was our oh gosh, I didn't even record it. Okay. What was it? Well, let's go see. If it's a transformer, what method should it have? Transform. There ain't no transform. What is there instead?
Fit.
Ladies and gentlemen, there's a fit. Why does this count vectorizer have to be fit? To what does it have to be fit? We saw it before. To what does it have to be fit? To a data frame to extract a what? A model. And that model, remembers, begins with a V, ends with a Y. It has a B in the middle. Vocabulary. Ladies and gentlemen, it needs to extract a vocabulary. But notice, we've just used it here. It's going to be part of our pipeline. An estimator, we're going to have in our pipeline transformers. Things like tokenizers, stop word removers. Things are already transformers. Then we're going to have some in our pipeline estimators, like this, which knows how to produce a transformer once it is fitted. And also logistic regression will be like that. It knows how to produce a logistic regression model once it is fitted to some data. Those are all going to be part of our pipeline. And then when we fit the pipeline, all those are going to be fit, and resulting transformers will come, and those will all be bundled up in the model, so that when we apply that model to another data frame, it just acts as a transformer. Yes.
So
Once we fit the model to another data frame, it yields a model, just like any estimator. Yeah.
So to speak of any logic things in this framework, any logic model, as Winchell was trying to do, is a transformer, but every experiment would be an estimator. Because like calibration, it has to be returns a model.
Right. Calibration would return a model.
Optimization would do it. Monte Carlo, well, maybe. Actually, that's interesting. What would and would not be an estimator is an interesting thing to think about. Because like a particle filter is an estimator, but
Yeah.
we don't have a good way of actually making it not a transform in its own right currently.
Yeah, and there are certain things in Spark ML that don't fit in that framework, like a evaluator. It's not a transformer, it's not an estimator, it's a different sort of thing. And it doesn't fit right now into a pipeline. But it does fit into another higher level construct, which is a cross-validator. So, and a cross-validator can go in a pipeline. So, anyway, okay, so now, ladies and gentlemen, we have a bunch of preceding steps. Now we're going to put in place a logistic regression. Okay, here we go. Logistic regression. Right, like that. You'll notice I commented out some parameters. We can come back to them, but for now we'll leave it. Okay? There's our logistic regression. Do you see that? Is that an estimator or a transformer? Logistic regression. Is that an estimator or transformer? It's a...
Actually, it's an estimator.
It's an estimator.
Because you have to fit it and then it returns the model.
Right. It doesn't it's not a transformer. It has to be estimated. Right now, it has no sense of what the logistic regression model is, or even how many parameters it will have. We have to fit it to a data frame to give it a sense of that and to train it to recognize that data frame, to recognize items. That's training. And then we'll go transform it, okay? But it will all be part of a pipeline. So having done that, let's create a pipeline. And this pipeline is going to have many pieces to it. Here are the pieces. First, it's going to have a word splitter. And then it's going to have a trivial word remover. And then it's going to map the words to the presence or absence in a vector. Actually, I think it's to the count that they occur. And then it's going to perform a logistic regression. Now, this third one, this map words, this one is an estimator. Remember that. Don't forget that. That's an estimator. Map words to presence absent vector. By contrast, word splitter and trivial word remover, those are transformers. Those work right out of the box. This guy is an estimator. So is logistic regression. That's an estimator. Both of them are estimators. And what's going to happen is when we fit the pipeline, both of those are going to be fit. And we're going to get back a model that incorporates all of them and knows how to split up words, remove trivial words, map the words to presence absent vector based on the vocabulary that was recorded when it was trained, and then perform logistic regression as a result with the trained model. Okay, ladies and gentlemen. So that's a higher level construct, and it's a construct that bundles these together not only for training, but also for testing of the resulting model, incorporates them. Next, we are going to fit it as befits it to a logistic regression model. Okay? So it is being fit to all tweet texts. What is it doing? Well, remember what all tweet texts look like. Remember, it's a value and a label. This is fitting the logistic regression model and the vocabulary. The vocabulary for that count vectorizer to this data. Ladies and gentlemen, it fits it. Ladies and gentlemen, it fits it. Okay? There we go.
So we need to create one thing that will do it for anything called fitbot. This one's Fitbit.
Yeah.
Or maybe we can call it Fitbite.
Okay, so ladies and gentlemen, now, this is a bad name on my part. This is logistic regression model. from pipeline. And that's kind of true, but it's with a pipeline. That's the point. It's not from the pipeline, it's with pipeline. Do you understand the significance? It is bundled with the pipeline. It's not like it gives us back just the one at the end. It actually gives us something that remembers how to process the data that it needs to eat. In short, to transform. Here we go. So, logistic regression model with pipeline. Boom. I'm gonna refit it. Okay? As fits the situation. And now I'm going to transform, ladies and gentlemen. Here's the DF logistic regression from the pipeline. Okay? So we just transformed the tweet text. Now you'll notice we're doing this in all text. We'll come around to do it with a subset. Just a few minutes here. Now let's do a classification. Binary classification evaluator. Here we go. Here's our classification evaluator. Getting ready to apply it. Now, ladies and gentlemen, it's time to evaluate the logistic regression model.
Yeah, wow.
97%. Okay, now we have every right to be skeptical. After all, we just trained this thing and tested on the same data set. Let's test on a different subset, shall we not? Should or not? Should. Okay, thank you. Thank you. I appreciate the confident response. Okay, so we split up that data set into DF labeled, I don't like this, DF labeled subset 1. So we're going to fit the model. Remember, we're going to fit and transform. We're going to have a model that's, remember, fitting is like training here. We're going to train the model, including the vocabulary, on one subset and apply it to the other. Should we not? Should or should not? Thank you. Okay. DS labeled subset 1. Bad name. You could readily prove that, I'm sure. Logistic regression model from pipeline, and I'll say trained on 1. Yeah, I know it's okay. It's DF. Oh man, I call it DF labeled subset. Well, fine. It's fine. Time is running short. DF labeled subset. Okay? Subset 1. So here we're fitting that whole pipeline, including the thing to turn words into vectors and the logistic regression model on just that first subset of data. Okay? And now, what should we get it to transform? The other data set, ladies and gentlemen. Ladies and gentlemen, the other data set. Okay, so we just fit it, and now, as befits our situation, we will go and give it the other data set. Okay? Labeled subset 2. We're going to have it transformed. And which one are we're going to do the trained trained on 1. Okay, why isn't this auto-completing it? With pipeline trained on 1, and we're going to set that to DF logistic regression from pipeline trained on 1. Okay, here we go. Hey, oh, okay, I must be misspelling something. Logistic regression model from pipeline trained on 1. Why isn't this? Okay, what's going on here? What's going on? Okay, here we go. Boom. I must be misspelling something. Here we go. Ready? Here we go. There we go. Boom. There we go. I still don't know what was misspelled, but it's fixed now. Okay, so here we go. DF logistic model from pipeline trained on 1. Are we okay with that? So we trained it on 1, data subset 1, and we transformed it to 2, and that gave us this. And what do we now have to do?
Estimate it.
We have to evaluate it, ladies and gentlemen. So we'll just go and we'll evaluate it. Shall we not? Thank you. Thank you. Oh, wait. So this is, so we're going to, don't ignore that because that was from the earlier result. We'll do it based on this. The results. Here we go. Oh, I forgot the D. 69%. Not as good. Not nearly as good. Let's do the reverse. Let's divide it up to fit it on subset 2 and train it on subset, yes, train on subset 2. You could say it either way. And then let's transform subset what? Subset 1. Okay?
Doesn't this imply that we're overfitting it?
I want to see which, yes, it does imply we're overfitting it, yeah. Okay, here we go. And drawing that. Here we go. Here we go. And ladies and gentlemen, that's our DF logistic, and we will go now. Oops. Same. 64%. Okay. So limited accuracy when we're doing it whole sections, half and half. Presumably in part a reflection of the fact that if you reduce the data by half, now you're going down from something like 100 health-related tweets to like 50, and you're getting a lot less variety with them. Okay, but we've been doing a lot of things by hand, ladies and gentlemen. Too many things, in my view, by hand. I'm going to, by the way, paste this in so I can amend this before I post it again tonight. Let us go in and define actually, before we do that, let's go to the one that we created first, logistic regression. This gets to Scott's question. The very first one we created, logistic regression model with pipeline. That was the one we created with all of the data. Logistic regression model with pipeline. We fit it to all tweet texts and had that 97% accuracy. Let's go see what it used. What were its findings in terms of?
What were the strong words?
Well, okay, so we'll come back to that in just a sec. But yes, that'll be part of this. So how long was the pipeline? 4. The pipeline had 4 items in it up here, okay? It had word split remover, trivial word remover, map words, vector, and logistic regression. Great, ladies and gentlemen. Now let's go and extract the parameter map from the last of those stages. What is the last of that stage? That's the logistic regression. So here are sort of the parameter used for that logistic regression, okay? By the way, it's a max iter of 100. We used 100,000 the other day, I think. We might have been able to do better, but time is of the essence. Next, we're going to go get the best model out of the pipeline, okay? We are going to extract the model that was fit. And how we do this is we extract the third stage and we say, treat this as an instance of a logistic regression model, okay? Stage 3, okay? You'll notice if we said stage 3, it would tell us this is a transformer. Here we're saying we know it's a logistic regression model. This is this best LR regression model. Let's go ask what the coefficients of that are. What are the coefficients associated with different words for this? Well, it's a long vector, ladies and gentlemen. A long vector associated with this. Let's go find the largest coefficient. So coefs equal that. I'm going to say coefs at argmax. What's the largest one? 110. One of these coefficients, ladies and gentlemen, is 110. Generally, the ones that are negative, these are the betas in logistic regression. The ones that are negative means if that word is present, it suggests a lot less likely, well, these strongly negative ones, a lot less likely that it's health related. The ones that are very positive suggest it's very, much more health likely. Okay, let's go get the vocabulary out. Let's go extract the vocabulary here. So this is exactly what Scott was asking about. Can we go find out the characteristics, or is this a monolithic, opaque thing we can't reach into? No, we're reaching into it now. Here we went to stage 2, and we got the count vectorizer model. That count vectorizer model, where did that come from? Whence did that come, that count vectorizer model? Did we give that to it? When we created the pipeline, did we give it a count vectorizer model? What is this thing here? This is a count vectorizer. Is it a count vectorizer model?
No.
No. Where did that count vectorizer model come from? Whence did that come? It came from fitting the pipeline. And it was generated automatically in that pipeline by virtue of fitting. And we have extracted it from the model that includes the pipeline. The model that resulted from that fitting is a pipeline that knows how to transform data frames given to it to data frames put out. On each stage of it is a transformer. And 2 of those transformers are things estimated from the corresponding estimators we told it to use. So when we fit that pipeline, it created those transformers, because fitting an estimator with a data frame gives you a what? A model, a transformer back. And this is the transformer that came back as this count vectorizer model. So we want to know, hey, let's go get the vocabulary of that model.
So what you're saying is that a pipeline can be given either a transformer or
Yes.
an estimator, and if you give it an estimator, it knows it has to fit it so it can
Yes.
get a transformer.
That's correct.
So this is basically a composition.
That's
You're just composing
That's-
transformers.
Yes, that's correct.
Or things that can
That's
be
right.
fit
It's a
into
pipeline
transformers.
of transformers now that resulted from fitting this pipeline of transformers and estimators. Yeah.
Huh.
And that pipeline of transformers and estimators was used to determine successive stages of processing, the data frames that were used to fit the estimators in there. Right? Okay. So ladies and gentlemen, here's the vocabulary that it deduced based on Twitter observations. You could see something about political discourse in the US right now. RT, sick, voted, millions, people, ill, illegal, Trump, I'm illegally, think, it's, vote, president-elect, votes, get, in, millions, love, illegally, popular, without, feel, evidence.
Is there
Illegals, too, sick, school, need, sensitive, team, your, disturbing, election, electoral, false, falsely. Sorry.
Is there a transformer that can remove punctuation?
Probably, but you could create one.
Because we have an illegally, we have an illegally comma, we have an illegally
Yeah.
period, and those really
Right.
should be put together.
Yeah, there are things I think which, and certainly if one doesn't exist, you can create your own transformers,
I mean,
no
it's
problem.
Expression, right?
And then you can put them into these things. But I think there are things that remove stems, that stemize things, so they turn sickness and sickly and not sicked, but sicker to sick.
I see.
Yeah, and stuff like that. Okay.
If I look correctly, if I look at this, shouldn't the numbers we're seeing in the upper one correspond to the weight that's given to the word in the lower?
Yes, they should.
That means sick has a negative weight.
Yes, it is a slightly negative weight. That's right, a small negative weight. Yep. And we'll see it's not very diagnostic, because there are people saying that is sick or something like that.
So in this case,
Or that so-and-so's got sick policies or whatever.
So if we'd gotten trigrams, one, we'd have a much larger vocabulary.
Yeah,
And two, we could distinguish between that is sick and I am sick.
that's true. Yeah, that's right. That's right. Yeah, that's pretty interesting.
Interesting.
Okay, so ladies and gentlemen, let's do this. Let us look up the word that seems to be associated with the most significant predictive capacity.
Okay.
Okay? Going out a bit on a limb here. Mental. This is associated with,
You can tell that Twitter's dominated by Americans.
yeah, mental. Okay, now let's look at the ones that are highly predictive. So the argmax is 110, okay? Let's look for all that are over 100. Let's go see. So this coaufs.to array, we'll go analyze what this does here, okay? What this is doing is it is getting, what is this doing? It's taking the coefficients, turning them into an array, zip with index. Does anyone remember what that does?
Zip takes two lists
Yeah.
and combines them into a tuple,
A list of tuples. So if I have, vector of 1, 2, 3, and a vector dot zip with a vector of, I think I should be able to do this, A, B, C, what will I get out?
1A, 2B, 3C.
Yeah, 1A, 2B, 3C. It zips them together.
That's
Now,
a wonderful case class.
no, how if I
statement.
do with index, what do I get? Well,
Right.
1 goes with 0, 2 goes with 1, 3 goes with 2, because this is the index of it, right? It might have been better yet if I had done this first, so it would be less confusing. Dot zip with index. So as if I have a whole vector of indices, 0, 1, 2, 3, 4, 5, and we're zipping it. So A is with 0, B is with 1, C is with 2. Do you see that? Okay, so this thing is zipping up each of the elements of the array with the index accordingly. That gives pairs, each of which one is a value, indicated the coefficient,
And one is the index.
and one is the index. And if the value is greater than 100, I say, go look up in the vocabulary what that word is. Okay, so here are the words that, for some reason or other, seem highly predictive. Child, medicine, fever,
Again.
mom, illness, day. Yeah, I don't know about again. I mean, that seems...
Well, it's a period. It's an again at the end, so I'm sick again.
That's true.
Okay.
That's
so
true.
it's-
Medicine is another one. Yeah. Okay. So ladies and gentlemen, yeah, that's so I don't know if there's any multiple. Yeah, even over 105. Yep. There are some. And nothing over over 110. Okay, I thought we did argmax was 110. Okay, I'm confused. Is there something over 140? Yeah. Mental, getting, fever, hope, I'm, home, child.
I think the 110 was the index of mental, not its value.
Uh,
Or was that the no? You actually are back.
no, mumble. Nothing over 200, right? Over 160 here. Mental, getting, hope, home. Highly predictive. How about things that are highly unpredictive? There are things that you can use to think it's very unlikely. And this is where it might get ugly. Less than 100. Yeah. School, back, support, babies, man, sense. Yeah. And some that I
Really?
won't even pronounce.
Producing babies is not predictive of health, but child is.
Yeah. Yeah, it is pretty interesting. Yeah. Okay, finally, well, you have buses to catch. We've been over these before. Cross validations. I set up a cross validator here, but the important thing with this cross-validator, ladies and gentlemen, is that I create this cross-validator using as its estimator for the cross-validator. Remember, a cross-validator needs a couple things to be specified. An estimator and an evaluator and a param grid and a number of folds. Needs a number of folds over which to perform it. Here, the estimator is the pipeline, the whole pipeline from start to finish. Reading, transforming the data, etc., turning them in. And because we are slicing and dicing the data into different subsets, and for each of those subsets, remember, we are going to apply this. It should be clear here. We are applying this pipeline, applying this cross-validator. We are applying it to all tweet texts. So in order for the logistic regression model to do its job, it has to process it into vectorized words, remove the stop words, because we're giving it the original tweets.
How can a pipeline be an estimator?
Because you fit a pipeline to a data frame,
So,
and it yields a model. Remember? We did that earlier.
well, yeah, but it's just, I mean, if you think of a pipeline as a series of transformers, the end result of it is an estimator?
No. Before you get the series, the pipeline is not the series of transformers. The pipeline model that comes from fitting the
Okay.
the
Okay,
pipeline
fair
is a series of transformers. Remember, that's why earlier we had our pipeline and we fit it. So here's our pipeline with these stages. Before we could apply it, we had to fit it to a data frame, and that yielded a model,
Okay.
a pipeline model that knows how to transform from start to finish, from soup to nuts, from splitting the words to removing the trivial words to mapping the words to a vector to logistic regression. It knows how to apply that all along those stages. And that's why it's an estimator, because it can be fit to, it can be trained on this. And exactly that's what we're doing in cross-validation. We are going to be training this on different subsets of the data and testing it on different subsets in 10 stages. Do you see that?
Mm-hmm.
See or not? Now, this is a better test than just dividing the data in half, because we're going to be able to try it with different subsets of the data. It's a more reliable thing. Here we go. Let us fit it, ladies and gentlemen. Fit we can, fit we will, fit we must. Okay? We are fitting it here to this data frame of all tweets. Why all tweets? Because it is internally, this cross-validator is dividing them up into 10 different subsections, taking different parts for training, different parts for testing. That's all part of what it's doing as we speak. Okay? It's going through and doing that. It's going to be fitting it in different components. And then we're going to be asking, what are the metrics coming out of it? What are the best models coming out of it? And we're going to ask it a little bit about transforming it, and we're going to evaluate it. Okay, we're going to evaluate the results. Okay, this guy is working hard. I don't know, are your guys still working? Oh, man, this is this. Okay, I don't know what that is. Oh, that's me catting all my output from that I've harvested over the past. Okay, I'm going to go through and classify some more. Okay, mine is working pretty hard. So maybe while this is working, in the interest of letting you out of here, if not on time, at least closer to time. I see, yeah, a lot of work's going into the recorder and that, okay? While that's working, I'm going to make some closing remarks for this class. And these remarks are going to be at a very high level. But they are due, I think. So first of all, I want to thank all of you for bearing with this class and all its limitations. and the fact that there's lots of issues still to work out with it. This is the first time I've ever taught the class, first time I've created the class, and it has been a learning experience to figure out how best to present this material and to cobble together the example. So I want to express my appreciation for you bearing with the limitations to my teaching in this regards. But we've seen in this class a lot of themes. We started with functional programming in Scala and looking at Scala as a language to help us reason about functional programming concepts, which I think were new to many of you. But a lot of that was motivated by the desire to use them in Spark and to use them in this context where they're so keenly needed. Distributed computing, memory-limited computation, using streams to conserve that amount of memory so you can pipeline operations, so you can throw data sets away and recreate them at any time by having a full lineage. And so the code's dependencies are very clear, and in terms of parallelizing it, it's a much easier task. Parallel programming is much easier with where dependencies are clear, and functional programming helps make that possible. But other overall themes, have to do with creating abstracting chunks of work at different levels, defining functions and higher level functions that take functions in or return functions, like that integrator function or differentiator function, for example. And defining abstractions in ways suitable for circumstances. Like the abstractions in Spark are meant for performance support for often iteratively intensive algorithms in a clean and transparent way. And I think they pursue their jobs admirably well. The benefits of functional characterizations of algorithms, we saw that throughout the term. The cleanliness that can come from composing functions and pipelines, for example, that can come through passing functions as arguments and returning functions as closures. These things are very powerful tools, closures that encapsulate state, and they're very much part of the Spark and distributed computing context here. These are tools which for many years were kind of not in the main light of commercial software development because very expedient, apparently pragmatic, but I would argue misguided attempts were to make use of languages that were much closer to the metal and were had less support for high-level software engineering but not a thought that would make the programs faster. In fact, from a systems perspective, a system science perspective, often we can gain the biggest speed-ups for our programs, particularly these days, the greatest performance by making use of languages that are clean, elegant, allow us to well-structure code, rather than relying on low-level coding to get us the performance. Low-level coding can get us a certain amount of performance, but often what really makes a program shine is the high-level algorithms, its ability to be parallelized these days, its ability to take advantage of parallelism both on a machine and on distributed sets of machines, and the ability to focus the time on really optimizing the core algorithms that may make the performance difference, rather than just making the whole thing a little bit faster with optimized C code or what have you. Those of you who are in my class 816 will know that actually tools like Java and Scala can actually be quite performant with fairly optimized C these days. And down the road, increasingly what's going to differentiate very performant systems is not going to be the low-level languages used throughout them, but rather using the right language for different components of the program and using languages that allow for exploiting things like parallelism, using less memory, etc. The tools that we've used have also been great for helping us advance data science at a practical level when it comes to joining together very large data sets in ways to confront our group. And I'm really excited by these tools for the possibility of making feasible certain types of analyses that would require much, much more effort, time, and slow down the learning loop if applied with traditional technologies like traditional SQL databases. So these tools have also allowed us, while relying on novel technologies like Cassandra or Hadoop or what have you, these tools allow us to express our algorithms in ways that are simultaneously familiar, fairly familiar, very clean, quite self-descriptive and elegant, performant, and easily modifiable. And those are an extraordinary set of combinations of characteristics compared to having to do MapReduce by hand in an explicitly parallel context in Hadoop. Our class has not had the chance to really delve into, in depth, any one of these topics. Winchell tells me that there are 3 courses on Coursera. I think three alternative courses, or 3 courses that you can take each one and still get more, taught on functional programming and Scala on Coursera. Spark is a large area. We've touched kind of the software interface to Spark, but there's a whole distributed computing side to it that's quite intricate. And actually, if you go to the code base for some of these algorithms, you can go browse the code for logistic regression models on the Spark sources. It's open source. You can go look at it. And what you'll see is there's a lot of effort to go into getting that right in a distributed computing context, go into coordinating, training a common model across data sets spread across many machines. This is not a small thing. We are doing it here very conveniently on single machines, but if we were using all of Sphinx and we still wanted one model to come out of the training that we're undergoing here on this data set spread across many machines, that requires a lot of coordination behind the scenes. So what's underlying this? It's easy to forget the level of sophistication that we're commanding here, but it's a level of sophistication that has depth I couldn't cover in the course in terms of the hardware side, the distributed computing side, the side having to do with concurrency and really leveraging that concurrency to the fullest. We didn't have time to really go into that. But the basic mechanisms you've learned are quite scalable. That's the good news. In contrast to issuing SQL queries against large Postgres databases, as the amount of data there grows, you really run into profound performance constraints. And here we're riding atop mechanisms like Cassandra, but doing so in a way that doesn't require us to engage in really low-level understanding of those mechanisms. We can describe things at these nice high levels we've been seeing today with our code here to train models, to apply models, with the confidence that that code is going to be able to run across many machines if required. But because I've not dealt with the full generality, you will find that there are additional performance-oriented considerations that come in if you are farming this out across large machines, and you'd want to learn about those too. But this is highly scalable stuff. It is powerful stuff. It is beautiful stuff. And it's given me profound pleasure to be able to show some of these techniques and some of these ways of pursuing computation with you. I've been doing this now for about 30 years. My first programming course at MIT was on functional programming in Scala back in 1986. And oh boy, did it exist. Scheme was invented in 73 or something, sometime in the 70s. And so I've been doing this for a while, but it is just such a pleasure to see it emerging into the mainstream, to see it be an extremely hot technology, to see it be so critical to our research. Something that simultaneously is so beautiful, so powerful, and so utilitarian, so extensible, so practical. So, ladies and gentlemen, we're just going to finish up here with a few commands. We have just fit our data set, and here we go. So this is cross-validation metrics. Here are our metrics across many items. So we're getting about 78% across the cross-validation. Looks like it appears we're getting about 78% accuracy. We're going to ask for the best model here, okay? And we're going to use that, the logistic regression model, from our cross-validation. Remember, this cross-validation was taking place with an estimator, and then to evaluate each of the subsets of the data, that was itself a pipeline. So we have composed these higher level structures, a pipeline on the one hand and a cross-validator the other, together in a way that is really really very, very powerful. And we can ask, for the param map that was used along with that. Okay, although that's a param map for the entire series. We could have asked for its stages. Now let's go transform with the best model. Let's go transform all the tweet texts. Okay, with the model that came out, the logistic regression model from the cross-validation that we asked for from the best model from the cross-validation. Remember, the cross-validation here, as was pointed out, is simultaneously performing cross-validation while changing these parameters, these normalization parameters. Yes, Scott?
Does this mean was it doing cross-validation on the intermediate steps of the pipeline? Since there's estimators inside the pipeline, was it actually like doing cross-validation?
Yes.
For
It kept on, for different subsets of data, it would re-estimate the model and apply that model to the other set. Yep.
I was wondering if we could do a cross-validation on the actual, vocabulary.
Yeah, we could. I've just shown 100, and it looks like it's got many, but it's off on some. Let's ask for its evaluation. Here we go. 90%. 90%, ladies and gentlemen. And we could, of course, we could go once again, get the model, find the words that were most predictive, but I imagine we'd see some similar words. And the words that are unpredictive, we'd see also similar words, which I'm not interested in re-showing. So, ladies and gentlemen, here we have a predictive model of the best model that emerged from this. The other beauty is, though, I'm not going to show it here, but you can save these models away. You could say, save this, persist this model away. And then, as we were reading live tweets in, just before we read live tweets in, we could read that model from persisted store. It would be reconstituted. This kind of freeze-dried model was saved away. It would be reconstituted, and we could apply it to the tweets as they come in to classify whether they're of interest or not. So these models can be persisted to a store by writing them out.
So once we apply the model, and we can actually classify these tweets, we could then take the tweets that were classified with a 1 and then basically dump them somewhere. So we basically have a continually growing number of tweets that are health related.
Yes, and we could, for example, restrict them to tweets from jurisdictions of particular interest and save them away on a daily basis into a growing database, which we could mine at our pleasure.
Well, why not just take all of them and then just filter the resulting data set based on location?
We could do that. It's just that it's going to be much more sustainable if we want to go through Twitter libraries to ask about, we're not going to be able to get it to give us all tweets worldwide within a certain area. We might be able to get it to give us all tweets for a certain defined region worldwide of particular interest, and we could then save those tweets away that are plausibly health related. And we could continue to refine our models over time. Okay? So this model for cross-validation, turns out we can write this out to a disk, save it away, load it back later. Okay? So, ladies and gentlemen, it is with that interesting illustration of elegance, clarity of code, the power of composing abstractions in a functional context that can be easily distributed, and a new generation of technologies that is open to the lab. It is with those reflections that I close this course. So thank you so much for bearing with it, and it's been my great privilege to be with you, and especially on this night, even as it dips to 30 below, to be able to share with you this exciting work. So please be encouraged to get off before the buses become less frequent, okay? Because I know many of you have a ride home. And now I'll stop.